Welcome to the Friday Transportation Seminar at Portland State University. My name is Chris Monsieur. I'm a faculty member in Civil and Environmental Engineering. I co-organized the seminar this quarter with Professor Jenny Liu from Urban Studies and Planning. Today we're very happy to have three presentations from our own students who are on their way to the Transportation Research Board meeting with about 12,000 other transportation wonks next week. So these three students will be presenting at that meeting, and so they're going to give us a preview, dry run, a preview. And next week we will also have a set of three encore presentations from three students that gave talks at the meeting as well. So they'll each give about 15-minute presentation. If there's time in that 15 minutes, we can ask questions during that. But if not, we'll hold all the questions to the end so they each get their 15 minutes to practice. And I'll just introduce them all right now. We have Steve Gehrke will be going first. He's a PhD student in Civil Environmental Engineering. Then Katie Bell is a Civil Environmental Engineering master's student. And Chris Muhs will bring us up. He's a Civil Environmental Engineering master's student. And I'll let them introduce their topic in their slides. And so with that, I'll turn it over to Steve.
Okay, hi everyone. It's good to see a good turnout here and give a preview of what I'll be presenting Monday morning at TRB if you're out there. Catch a second run. This is some research that I did with Dr. Kelly Clifton on an application of geographic perturbation methods to residential locations. And we used the Oregon Household Activity Survey, which is a data source some of you may be familiar with. And this is a proof of concept. The importance, so why do we do this research? And the idea behind it is that we have this travel survey data that we want to release at a very disaggregate geography. The reason for this is that if we're interested in non-motorized travel and its influence with the built environment, we want to be able to make kind of a one-to-one correspondence. Instead of looking at this data aggregated up to a larger TAZ or a geographic scale, it doesn't really reflect the real relationship that's going on with the built environment. But however, there's this problem of releasing this data set in that it kind of compromises the respondent's confidentiality if you're putting their point and making it available to everybody out there. And so we need to consider this problem in this research, and that's what we're hoping to do here. Obviously, we're also not the first people to think about this. This has been done in public health research and computer science research, and so we sort of borrow some of the concepts from these disciplines and utilize them in this study. Okay, and so what is geographic perturbation? Well, it's essentially displacing the geographic coordinates of a household location. So you do something to the XY location that now moves it into somewhere else in the geographic plane. In doing this, you can imagine there's some sort of trade-off that takes place in that you take the location, you move it far enough away that you preserve this anonymity and you kind of minimize this disclosure risk. But at the same point, if you move it too far away, now the context that the environment surrounds that household location is no longer necessarily accurate. So you want to find that kind of sweet spot between the two of keeping the utility of the data high, but also minimizing the disclosure risk. And so some objectives of this research are that we reviewed some of these methods that were used in public health research, and then we ultimately selected one of them and demonstrated a proof of concept through some sort of brief empirical application. And so to kind of run over some of these perturbation methods, the first of which is aggregation. And so if we've dealt with travel survey data, you may be familiar with this. The figure on the left represents zonal aggregation, and so those three households now get aggregated up to a larger geography, and so that geography, that TAZ, contains three households. So we're familiar with that. Or you could do something similar like on the right, where you take those and reflect them as what appears to be a disaggregate source, but really is just an aggregation. It's a centroid that now reflects three household locations. A second category of perturbation methods are these affine point transformations, and there's three separate techniques within that. The first of which is translation. So you take the XY coordinates of the original household location, and you either add or subtract some sort of constant to it, and it has this effect of either laterally shifting up and over the coordinates of the perturbed location. Also, you can do something to the scale, and so instead of adding or subtracting a constant to the original XY coordinates, you can now multiply a factor, and this either has the effect of kind of expanding out the jittered location or contracting it back in. And finally, the third affine point transformation is the rotation one. This was a little more difficult to see, but you kind of pick a spot in the center of the, wherever in the map it may be, and kind of rotate, and now you have the jittered locations. And so probably as we're going through this, you can pick up some of the shortcomings of these different perturbation methods. As I kind of explained with method 1, you run into this ecological fallacy in that you're taking the individual units and you're aggregating up, and you're losing something with the data by doing that. Also, if you're looking at a really large geographic scale and trying to capture the built environment, you're missing some of those fine connections that are being made. And so there's a limited transferability, and it's kind of insensitive policy if you're looking at non-motorized travel. So the affine point transformations, now you have this appearance of a disaggregate data source, and so this avoids this sort of aggregation problem. But as you probably took, that if you can figure out one of the one-to-one correspondence for one observation, you can do it for the entire data set, and that doesn't really do much for the anonymity. And so the answer to this is to somehow randomly relocate these household locations by a process called jittering. And so don't have much time to kind of go through these different techniques, but the takeaway from this is that you kind of have some sort of predefined boundary, and you spatially mess with the XY coordinates to place it somewhere within that boundary. But the problem that you can see kind of in this example here and this example here is that, well, you could perturb it, and it could end up very far away from the original household location, but since it's random, you have also the possibility of landing right directly on top of it, and so that does nothing with the anonymity. You now have a jitter location that falls directly on top of the original household location. And so kind of a workaround for this was recently introduced in the public health field, and this is something called the donut masking technique. It's a very nice name, and probably better illustrated through the graphics in the following slides, but essentially you have this inner ring radius, and you have to move it, the household location, far enough away that you preserve this anonymity, and it's up to the data custodian to sort of choose what's appropriate. But you also don't move them so far away that the utility of the data is lost. And so just to kind of walk you through it, you have this original location there, and you then create this donut sort of around it, right? And so you have that white area the house can no longer be relocated within, but in this band, this donut around it, there's an infinite number of possible positions. And so you get some households there, and you randomly select one of them within there, and presto, you have your jittered location there in the red. And so having selected this, we went ahead and went with a brief empirical application, or this proof of concept. And so just to start off, we selected just 10 households in the Oregon Household Activity Survey data sets, and we selected these in unique census tracts or neighborhoods, and these varied by population density and their access to rail. And so we kind of got a good variation of sources to look at this data utility and this disclosure risk question. And looking at the data utility, we looked at 8 different built environment measures, 4 of which are density measures that are measured at a half mile around the original location and the jittered location. And so these are the population density, employment density, jobs person balance, intersection density. And then 4 distance measures, which are distance to the nearest park, nearest grocery store, and nearest rail station, bus stop, excuse me. And these data sources came from RLIS and the United States Census. So there's kind of an idea of the different neighborhoods we looked at. And so you can see sort of Sherwood and distant Washington County and Wilsonville kind of represent a more rural context. And then you have a household that we selected randomly within the Portland State area, and also in Northwest 21st, 23rd, that's more of an urban context. And so selecting these 10 different households, we tried 4 different trials, so 4 different combinations of donut sizes. With inner ring radius, that was 0.5% of the census tract population and 1% of the census tract population. So the greater the percentage, the more houses that you're hidden amongst. And then to measure among the 100 simulated perturbed household locations, we used something from computer science research called the K-anonymity statistic. And this was proposed by Sweeney in 2002. And then on the flip side, we looked to using a half mile and a 1 mile outer ring. And this is typically used in non-motorized travel, so many of us are probably familiar with that, to kind of give that outer ring. And to measure variation between the original location and the perturbed location, we looked at the root mean squared error. And so here's kind of an illustration of it. So the top 2, you can see, have that outer ring of a half mile buffer, and the lower 2 have the 1 mile, so much further out, potential for displacement. And then the 2 on the left have the 0.5% inner ring, and the 2 on the right have the 1% inner ring. And so did this simulation 100 times and did these different measures. And I'm not going to put up the tables here for sake of time, and just kind of give you the upshot on what we found. And so with the disclosure risk, so looking at that inner ring, sorry, it's a little cut off at the top there, but the anonymity improved as the inner ring increased, especially for the smaller outer ring radius, the half mile outer ring radius, as you increased it from the 0.5% to the 1%. As you would think, you'll enable more distance for this house to be perturbed from its original location, so the anonymity increased and disclosure risk went down. However, the trend was less apparent with the larger 1 mile outer ring radius, and this is kind of an artifact of this indirect relationship that we selected for this proof of concept. So the 1% isn't really tied to the 1 mile, so as you saw in those latter two, there's a really large donut that you could choose from within, and so that's something to look further into. But also, we saw that as the outer ring increased from the half mile to 1 mile for all the trial combinations, the median K anonymity and statistic improved. So kind of makes intuitive sense that if you allow the house to go further out, you limit the disclosure risk. And then looking at data utility, overall the spatial error with the lower went lower for the smaller inner ring radius. This is especially true for those urban contexts and those more rural contexts, but we didn't really see that this hypothesized trend was consistent in the remaining tracts of those kind of in the outskirts of Multnomah County. So this is something that we probably will have to examine a little bit more. And then looking at the different contexts, more specifically with the built environment measures, we saw that the spatial error varied across the different contexts. So in the urban environment, we found more variation in the density measures, specifically employment density and jobs per person. Also in distance to nearest park, and that's kind of a wonky measure that we used, and I don't know if we'll use it going forward. But looking at then the more rural context, we found those households that are located in neighborhoods further from the CBD, that the distance measures kind of popped up as varying more often. And then finally, kind of three measures kind of popped out as being something that we could possibly use going forward, and these are intersection density, distance to nearest door, and distance to rail, because these consistently, as we went from the different trials, expanding the inner ring and expanding the outer ring, they held the consistent hypothesized trends that we would improve the anonymity and increase the data utility as well. So that's kind of the upshot right there. Next steps are this is just a proof of concept, and so we just looked at 10 households in neighborhoods. So we're currently doing it for the 3-county Portland region, so it's about 5,000 households. And then we'd like to obviously do this for the entire Ohio data set, which is 20,000 households, so this needs to be automated, and that's what I'm working on right now. And then ultimately determining some sort of best practice. So when do you use a certain donut size? Does it vary the measures you look at for data utility depending on the context? And so these we kind of have to go through and kind of process a little bit more. But ultimately, we want to be able to release this disaggregate data, and so we want to have model findings that show that, well, the estimates that we're getting from this more disaggregate data are better than what we've had in the past, so better than the TAZ released data, looking at the non-motorized built environment relationship. And then we hope that if we do release this, we're able to kind of have some sort of confidence measures that go along with it. So this is kind of like the American Community Survey does, where you have this margin of error that comes with the data you're receiving. And so something that would be useful to researchers and practitioners using this data. And then some thoughts as we go forward. This is just a couple of bullets, but there's many more that we have. We're looking specifically in this at jittering the household location, but there's definitely some credence to doing likewise to the workplace and the activity locations. If you know that a person works at a large employer in Hillsborough, you probably have an idea. Maybe they work at Intel, and once you figure that out, you can reverse engineer to find out their original household location, and so that has the impact of perhaps compromising the anonymity. So that's something to look forward to, that maybe you jitter both the origin and the destinations, and then the route would naturally be altered. And then also integrating this within survey design and data collection process. And so if we continue to go forward taking telephone surveys, then perhaps this doesn't go into the data custodians' hands, and that we just punch in the address and immediately it's kicked out as a jittered location. And so somehow employing that within the design is some additional thought we need to give. So with that, I'd like to thank Dr. Clifton for her guidance in this project, and our sponsors, ODOT and OTREC, for their funding and also their technical guidance. And I thank you guys for listening, and open up with any questions if we have time. Okay.
Amenities, employment, and retail at the end. Was that network distance? Or?
Yeah, no, it's straight line at this point, but yeah, definitely a network would be something to think
Okay, and so I guess the follow-up is for the jittering Did you do that with network nodes or just absolute locations?
So, I don't know if I completely understand, but so the jittered location, we would then take its distance to the nearest park, a straight line.
Oh, I
and
see.
we'd compare that to the original location's distance to the straight line, and so that we find some sort of variation between the two measures.
Oh, okay, sorry. I think I misheard your first answer. I get it now. Thank you.
Great.
Did you say that you only looked at 10 households?
Yeah.
And so why only 10 and why not 30 or something that would help you find more statistical significance in your
Yeah, I mean, it was a proof
evaluation?
of concept at this point. I mean, a lot of it was kind of finding, well, how do we go about jittering data? And so figuring out what technique made the most sense. And then, you know, there's deadlines for TRB and all this. But so once we came along with that, I didn't have this all automated. And so, yeah, it was really just this complex spreadsheets and kicking out from statistical packages. And so all at the time I could only do it was 10. But right now we're doing it probably at least 100 simulations and doing it for 4,800 households. And so we'll definitely get to find out if there's these same trends kind of hold.
Okay, thanks, Steve. We'll make the transition, get Katie set up. Is this one yours?
Yeah.
There's the clicker.
Okay. So I haven't gone over too much yet, so I think that's okay. So this is a system that ODOT developed. It's actually a smartphone application, and they developed it to simplify weight mile tax collection. So the smartphone application tracks the GPS data and then transmits it to ODOT. In February 2010, ODOT conducted a pilot project, or they started a pilot project, and 3 truck companies volunteered for the project, providing 15 trucks. And the movements of these trucks were recorded every 5 minutes for a year, and that's the data that we've been evaluating. So other research related to truck GPS data has mostly been done over the past 4 years. This provides a summary of the different research projects that we looked at, and it's a pretty good representation of what's been done. The columns show the different performance measure categories that each project addressed. So none of the projects address system condition measures, and this is likely because bridge wear is estimated using truck weights, and pavement wear is estimated using axle spacings, and this level of detail usually isn't available with truck GPS data. And for similar reasons, not much research has been done in the area of planning and modeling. A common use of smartphone applications in transportation are travel time estimates and emissions estimates. INRIX is the company that provides GPS data for the Urban Mobility Report, and ZATA Turnpike is a system similar to TRU. It's a company that tracks movements of trucks for truck companies and then provides optimization reports. And then eRoad's also similar to TRU. It's a system used by the New Zealand government for weight mile taxing. The fields shown here with the orange border are the cells that are available with each raw data record. So like most GPS records, you get latitude, longitude, and a timestamp. And then what separates this data from other GPS sources is the weight class of the vehicle and the axle count of the vehicle. And for each phone that the application's uploaded to, a unique device ID is shown. And then you can connect that data to data for each truck to get more information about the truck, such as a license plate. And the license plate is included in way and motion data, so then you can connect the GPS records to way and motion records, and a whole lot of other data fields are then available, such as vehicle type, vehicle class, but maybe more importantly, axle count and commodity code, gross weight, and axle weight. This is a histogram that was created using the GPS accuracy field of the data. So it shows that about 50% of the records were within 20-foot accuracy, about 75% were within 20 feet of accuracy. And the accuracy of the records ranged from 3 to 840 feet, but we only showed 80 feet on the x-axis because 98% of the records were within 80-foot accuracy. And this shows the spatial distribution of the levels of accuracy. And the important thing to take away from this is that the higher levels of accuracy, which are shown with the darker colors, are that the interstate corridors all have relatively high levels of accuracy. And this gives a view of where trucks traveled in the Portland metro area. So the darker levels show where trucks travel. The darker areas are the areas with a higher record density. And they're likely areas that trucks travel a lot, like truck depots. This provides an example of the ability to disaggregate, the level of disaggregation you can get with this data. So it's a map showing the record densities for each highway segment. And so the thicker lines are the highway segments that the trucks traveled on the most. And this is just for the 1030 weight class, which is one of the heavier weight classes. And maps like this could be created, and this kind of information can be you can get this kind of information from the data for any of the other data fields, such as commodity code or truck type. And with the ability to disaggregate the data to this level allows the development of trip generation rates. So for this is an example where we used ArcView GIS to get the proportion of records in for different weight classes in different land use categories. So the different colors represent different weight classes, and you can see that trucks travel more in the mixed-use residential areas than the rural areas, but heavy trucks in particular traveled more in the rural areas. So you can get quite a lot of detail that could be used to develop trip generation rates. And like I mentioned, mobility is an area that's been explored the most with past truck GPS data. This is a list of commonly used mobility performance measures that the data could be used for. And we compared space mean speeds estimated from the true data to those estimated from the portal system in the Portland metro area. And the portal system provides loop detectors So we compared those two speeds, and about 50% of the true records were within 8% of the portal speeds, and all of the true records had speeds within 25% of the portal speeds. But on average, true speeds were 7% lower than portals, and 80% of the true speeds were less than portal speeds. And this is actually consistent with past research with GPS data. Past research has shown that truck GPS speeds are typically slower than loop detector speeds, and this is because loop detector speeds measure the counts of all vehicle types, not just trucks. So it includes vehicles that are traveling slower than trucks. The colored portion of this map shows average speeds along I-5. So this is the Washington-Oregon border. So this is the northbound segment of I-5, and it includes the Columbia River crossing. So the red colors are slower speeds, and the green colors are faster speeds. And then the gray shades in the background are the same density map I showed before. So you can overlay the speed information with the density information to see what might be causing bottlenecks. So in this example, the slower speeds are shown right before this very dense area. So this is how the data could be used to analyze bottlenecks. And the map on the left is the same one from the previous slide. The map on the right, it's also a speed map, but it's a speed map created using a different method. For this speed map, we since the records are consistently 5 minutes apart, you can estimate speeds using record densities. So you can see the maps aren't identical, but the record density estimates provide a pretty close, a pretty reasonable estimate of the speeds. And within this method, you don't need highway mileages to estimate the distances between points, so it requires less data processing and less data in general. And this is a framework for an emission sensitivity analysis that we're working on. The orange boxes are data fields available with true, and the blue boxes are output. Our output from Muhs, we're working with a program called Muhs, which is the Motor Vehicle Emission Simulator. It's an EPA program to estimate emissions. And then the white boxes along the bottom are the variables that we're looking at in the sensitivity analysis. So with our preliminary results, we've seen that when trucks are fully loaded, the emissions rates tend to be 20 to 50% higher than when the trucks are empty for certain emission types like particulate matter. And then speed and grade have an even greater impact on emission rates. So when you combine errors in those vehicles together, it can have quite an impact on the accuracy of the emission rates, meaning that the details available with the true data could greatly increase the accuracy of emissions rates. And this is a framework we provided to ODOT showing different applications that the data could be used for, and the columns show the different data fields that are needed for each application, and all of those data fields are available with the true data. And we found that the areas that would benefit the most from the data are environmental performance measures and planning and modeling. So in conclusion, and these aren't all of our conclusions, but there's some highlights. The data is very valuable for a variety of different applications. Trip generation rates could be a great area for the data to be used. We just scratched the surface in this area. The method that we used to look at the potential for trip generation rates could be further refined, and the data could, the information from the data could be integrated with a model that ODOT's developed called SWIM2. It's a spatial economic model that could make use of better trip generation rates. And then we found that the data could be very valuable for mobility performance measures and could be used to look more closely at bottleneck case studies. And then it could also be used to increase the accuracy of emissions estimates. We found the emissions estimates are highly sensitive to grade, weight, speed, and truck type changes, which are variables available with the true data. And then with the estimations, the increased accuracy of the estimations, that data could be integrated into ODOT's green step model, which looks at the impact of different policy changes on emissions. And that model doesn't currently have much information related to heavy-duty trucks. So this could be very useful in that area. And I want to thank Surisha Couture. She's a PhD student here that worked on the emissions analysis with us. And the sponsors of the project are OTREC and ODOT. And also want to acknowledge everyone we worked with at ODOT. And I'll answer any questions.
I was curious why there was higher accuracy along the interstate. I think it was for location, more accurate locations.
I don't know that there, I can show you. So I don't know that there wasn't necessarily higher accuracy along the interstate corridors, but that we just were confirming that I think it was so this 98% of the trucks that the records that were within 80 feet, that had 80 feet accuracy or better, they were all along the interstate corridors. And most of the ones that were the 75% that were within 20-foot accuracy, those were all along the interstate corridors. And most of the data was within that accuracy, whether it was on the interstate corridor or not. But the ones that were not, the small portion that were not within that accuracy, were not on the interstate corridors. So, and some of the ones that were not were, they were next to cliffs. That was one reason that they, it's called the canyon effect. But generally along the interstate corridors, there was good accuracy.
Okay, thank you. So. We'll switch to Chris. All right.
Good afternoon, everyone. Nice to see you all. Thanks for coming. My name is Chris Muhs, and I'm presenting research about ITE trip generation. So ITE is the Institute for Transportation Engineers, and I'm introducing a proposal that is informed by a research project that we did last year. Dr. Clifton, myself, and Christy Currens. And we learned a few things from that project, and this research is to present a proposal for a new method to change the way that ITE does their data collection. So, for those who don't know, trip generation is what you do when you want to estimate how many trips, how much traffic you're going to get at a new site. And the ITE manual is the go-to off-the-shelf reference for this. So over several decades, they've collected over 5,000 sites worth of data and have developed methods. So it's very prevalent in the United States as the way things are done. But there's some problems with it. I'm going to talk to you about the biggest ones. So the biggest problems are that ITE developed its rates by observing data mostly at suburban locations that are heavily vehicle-oriented. So most of their locations were not in central business districts, not in very urban areas historically. So as such, they don't really give a lot of attention to the urban context or things like transit-oriented development or mixed use. And then the other major problem with the current method of ITE is that it's focused on vehicle trips and the peak hour of traffic. And the ITE method is also focused on the immediate adjacent roadway facilities. But we know from research that if you put in, let's say, a Walmart, that affects more than just the immediate roadway that's next to it. So the purpose of this research is to introduce a new way to do things. And our method is based on urban context, including all travel modes, including person counts, and considering more than just the peak hour of vehicle traffic. So the framework has 4 major components. 1 is data, 2 is revisiting the method, 3 is revisiting the analysis, and 4 is monitoring and evaluation over time. So the first thing is person counts. And this is important because if we count people, then we can get a better understanding of the overall effect of a new site, not just its effect on vehicle travel. And then once we have person counts, person trips, then we can assign those to modes after the fact. For vehicle counts, ITE already does this pretty well, we think. So they currently count vehicles entering and exiting a site, and then they also count the direction that they're going. So we also want to consider bicycles for this, as that is important in long-term planning as well. One major change that we're introducing is an intercept survey. So ITE currently does not require this. This is our big change. And the critical questions on the intercept survey would be the modes of travel, how many people were in the vehicle with you if you chose a vehicle, where you're coming from, where you're going to, how frequently you visit the site, and then socio-demographic information. And the reason for the intercept survey is that it allows a much more robust analysis of the important factors that are related to trips generated at a site. One big issue with the intercept survey that we don't have the answer for yet is the sampling design. So it kind of depends on the amount of people that are going to and from a site, how many you have to survey in order to get statistical significance with your sample. And then urban context is a big consideration. So we know from the literature that urban context has a relationship with travel. And we want to include that relationship, or at least our understanding of it thus far, into trip generation. So currently, a few cities and jurisdictions have developed their own methods to deal with urban context to bypass ITE altogether, but there's no consistent method to do so. So if for trip generation studies we collected more information on the built environment surrounding the site, then we would over time be able to use that data effectively. And then we have the site level attributes. So I think Steve's presentation was kind of touched on why the built environment is important, but one of the important characteristics is the design attributes, and that means site level things. So like the way the traffic is circulated through the site, whether parking is out front or in back, how much parking there is, all these things. And these factors aren't usually important in trip generation as it works right now, but we know that they are important when the time comes for developers to negotiate with jurisdictions themselves. So we want to kind of find out more about where the level of importance lies there. And we also know that the site level attributes relate to the overall urban context. So I guess a good example would be, if you build it, they will come. So you think of the Field of Dreams. Now, we know that just because you put a bike rack out front of some place doesn't necessarily mean that you're going to have a high level of bike mode share. You need something else surrounding the place in order to get that. So if we could collect this information along with trip generation studies, then it would help us become better informed. And now for background traffic, we know that ITE does this right now for the adjacent facilities for vehicle traffic, but we also want to gather data for the other travel modes. And then in doing such, we could get a better idea of how to implement things like multimodal levels of service, and then we could also revisit the time that is important to us. So, talking about the time that's important to us, currently it's the peak hour, but we did some research and found that the peak hour might not really be the peak hour for all people. It's just a measure that's usually for vehicle trips. So this plot right here, your x-axis is the time of day. Your y-axis is the percentage of the sample for that mode that was traveling during that time of day. So this data is from 2006 Household Travel Survey in Seattle, and this plot is for shopping trips. So we have the counts by the travel modes at the top left there. And then in red, we see the vehicle trips. In blue, we see transit. In green, we see bike. And yellow is walk. And what we see here, so the gray boxes are the 5 to 7 p.m. peak hour, and as well the 7 a.m. to 9 a.m. peak hour. And those are typically the ones that ITE uses. But what we're seeing here is that ITE's peak hours might not really be the peak hours for everyone. So yeah, we see on this plot that the bicyclists do have the most amount of trips in the PM peak hour, but for the other modes, that's not the case. And here's another plot from the same data set of dining out trips, so like going out to dinner or out for food in general, excuse me. And we see this one looks even worse. So we see that the most people walking for this trip type is occurring around lunchtime. So this kind of lends us to need to think about revisiting what really is the peak hour, or if a peak hour is really what we should be using to assess trip generation altogether. Now, for the project that we did, sure. Cool. Okay. From our survey that we did to inform this research, we used handheld tablet technologies to administer an Intercept survey. But these tablets are also useful for collecting other information, so things like site level attributes and parking and other things like this. And then to collect background traffic for not just vehicles but person trips, there are already instruments that are available that can do this passively. So this could save some money, and if the tablets and smartphone technologies are used, then the apps that you can develop could lead to standardization if they become widespread. So in conclusion, we want trip generation to consider all travel modes, all urban contexts, in order to make our policies better based on these things. So I forgot to mention this in the beginning, but trip generation is usually used for developer fees. So what that means is when a new business comes in, the developer is usually charged for the impacts to the transportation system that that individual business will have. So if we can make the method of assessment better for that process, then we can have a more efficient allocation of what the real impacts are. And then the other big thing is if this proposal were adopted, it would lead to a much better database. So if people were doing this all over the place, then it would kind of require an evidentiary base, so like a place to share all the data to inform research and to inform practice eventually. And we know that the data collection costs, if this is to be implemented, will go up. But like I said before, it would lead to a more efficient allocation of infrastructure provision, which would, we think, save money. And then monitoring over time is important. I think that a lot of researchers call for that all the time, and it doesn't always happen, but we are calling for that as well. And then we know that this is a proposal that for now is mostly focused on informing research. So over time, we would find out what the most significant things, what the most essential pieces of data are, and then we could streamline this process to be practice ready. And with that, I'd like to acknowledge the project sponsors and the folks who helped out with the research. And if you have any questions, these are our email addresses. So thank you.
In the beginning, you mentioned when you add a Walmart into an area, it doesn't just affect right around the Walmart. Did you guys propose a way to address sites or increased area around the site and how to interpret that?
I think the idea is, I mean, Walmart is one example of just one store type, but the idea is that, say you put a place, like a new business goes in to like the middle of a town. We know that that affects how people will travel within some geography around that place. So that's why we want to collect the urban context data to see what is really important there with the changes. Does that answer your question?
Slightly. I just like the areas like farther out than just right around. Are there ways of collecting data and knowing that that's attributed to that new development?
I think that there are ways of measuring, like volumes of traffic, on roadways that are beyond the immediate site. But if we had the origin and destination information from the Intercept survey that we proposed, then we could definitely assess that.
Actually, as a follow-up answer to that, usually those estimates, those trips are assigned to the network based on traffic data. So depending on where the routes are, you would actually estimate a greater number of trips to that business and where they're coming from. So that's how it's done in practice. My question is, sorry. My question is, so that Seattle data you presented, what type, like what land use context is that in Seattle? Is it overall types of trips? Because you mentioned, the land use context will inform when people are making those trips. Do you have any extra data that you can provide there?
So those plots were from the entire sample of that data set, so we didn't control in those plots for, say, more urban or more suburban locations. It's just the overall sample.
So right now you go to the book, you figure out, you go to the use, you figure out the trips. This wouldn't still be, you wouldn't be doing this after the impact was in place to measure, and you'd still be doing this on similar uses to generate a baseline so that when say a new store does come to town, you're not waiting until after they build and their impacts are established before you're measuring them. You're using that to build a bigger database.
So the book right now tells you how to go out and lay down a pneumatic tube to count trips in and out. We are proposing a way to collect data to change that method.
So for transit riders, they'll have to walk some distance to get to the stop. Maybe it's directly in front of their house, maybe it's 4 blocks away. Is there a certain distance, or do you have a methodology for if someone has to walk X 100 feet, it becomes a bimodal trip where they are walking and transit versus just transit?
That's a good question. So in the research that informed this proposal that we did, our Intercept survey allowed you to report multiple modes to address that very question. We don't have a definitive method like, yes, this is a walk trip, or no, this is a transit trip, but we've written another paper actually to address that very question that was presented at TRB last year. But there's no clear cutoff at this point. But typically for a thing like that, you would call it a transit trip. So if transit was used and walking was the only other thing used, then you would call that a transit trip. That's how it's done currently.
Okay. Before we thank Chris and then Katie and Steve again, next week's speakers will have again 3 speakers: Oliver Smith, Colin Rowan, and Alex Bagazi, talking about what they presented at the conference last week. So if you were a student and you asked a question, make sure, since I don't know everybody's names yet, make sure you come back and we get it checked in. If you didn't get a chance, just turn in a slip of paper with your name on it. And if you have any questions, Jenny and I, Professor Liu and I will be in the back to answer any questions you might have. So thanks. Thank you, guys. No, that's fine.